We've journeyed through the discovery of cosmic acceleration and witnessed the quantum paradox at the heart of empty space. We've learned that the vacuum is not empty, that dark energy dominates everything, and that the cosmic horizon is shrinking, erasing the universe's history galaxy by galaxy. But all of this has been leading to one inevitable question: how does it end? If dark energy remains constant or grows stronger, the universe's destiny is sealed. We're not heading toward a big crunch where gravity pulls everything back together. That fate has been averted. Instead, we're racing toward something colder, emptier, and, in its own way, more final. Today, we explore the architecture of doom, the slow-motion tragedy written into the laws of physics, the various deaths that await the cosmos, and the question of whether anything, even consciousness itself, can survive the end of everything. The universe is not just dying, it's being systematically dismantled, and we're living witnesses to the early stages of its dissolution. Start with the stars. They seem eternal on human timescales, but they're not. Every star is burning through its nuclear fuel, converting mass into energy through fusion. The largest stars burn hot and die young, exploding as supernova after just a few million years. Smaller stars, like our Sun, will burn for billions of years, eventually swelling into red giants before collapsing into white dwarfs. The smallest stars, tiny red dwarfs, can burn for trillions of years, but they all die eventually. In about 100 trillion years, the last stars will fade. Galaxies will become graveyards of stellar remnants, white dwarfs, neutron stars, black holes. No new stars will form because all the available hydrogen will have been fused into heavier elements or locked up in stellar corpses. The universe will enter what's called the degenerate era. The only light will come from the occasional collision of brown dwarfs, the rare merger of white dwarfs temporarily rekindling fusion, or the faint glow of proton decay, if protons indeed decay, as some theories suggest. But even these dim lights will eventually fade. White dwarfs will cool to black dwarfs, frozen remnants at the temperature of the surrounding space. Neutron stars will radiate away their remaining heat. The universe will become truly dark. But the story doesn't end there. Over even longer timescales, gravity continues to work. Orbital dynamics cause planets to either fall into their stars or be ejected into interstellar space. Galaxies themselves slowly evaporate as random gravitational encounters fling stars outward at escape velocity. In about 10 to the power of 30 years, galaxies will have mostly disintegrated, leaving behind scattered stellar remnants and central supermassive black holes. The universe will be a thin gas of dead stars separated by vast, growing distances. And still, the expansion continues. Dark energy keeps pushing, keeps stretching space, keeps increasing the distance between every remaining object. The universe becomes lonelier and lonelier. Eventually, the only significant objects left will be black holes, stellar mass black holes, formed from the collapse of massive stars, supermassive black holes at the centers of ancient galaxies. These gravitational monsters will dominate the universe. But even black holes are not eternal. Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation and slowly lose mass. This Hawking radiation is incredibly slow for large black holes. A solar mass black hole takes about 10 to the power of 67 years to evaporate. A supermassive black hole takes even longer. But given enough time, all black holes will evaporate. The largest ones will be among the last significant structures in the universe to disappear, converting their mass into a diffuse gas of particles and radiation. When the last black hole evaporates, in perhaps 10 to the power of 100 years, the universe will enter its final era, the dark era, the era of true nothingness. By this point, the universe will be dominated by dark energy. Matter will be so diffuse that it's essentially non-existent. Individual particles will be separated by distances many times larger than our current observable universe. The temperature will be a tiny fraction above absolute zero. In this state, nothing can ever happen. There's no energy gradient to drive any process. No particles are close enough to interact. The universe has reached maximum entropy, heat death. This is not an end in the sense of a final moment. It's an eternal state of stasis. The universe continues to exist and expand, but nothing changes. No stars shine, no planets orbit, no thoughts are thought. The cosmos has become a static void, empty of everything except dark energy itself. This is the slow fade to nothingness, the heat death of the universe, and it's written into the laws of thermodynamics as inevitably as tomorrow's sunrise. But wait, there's another possibility, one that's somehow worse. What if dark energy is not constant? What if it's increasing over time? Then the acceleration will become extreme, the expansion rate will grow without bound, and the universe will tear itself apart. This scenario is called the Big Rip. In the Big Rip, the dark energy density increases as the universe expands. This creates a runaway effect. More dark energy means faster expansion, which creates even more dark energy, which accelerates the expansion further. Eventually, the expansion rate becomes so extreme that it overcomes not just gravity, but all the fundamental forces holding matter together. The timeline of destruction is methodical and horrifying. First, about 1 billion years before the end, galaxy clusters dissolve. The expansion has become strong enough to overcome the gravity binding clusters together. Galaxies drift apart, each becoming isolated islands in an ever-expanding void. Then, 60 million years before the end, individual galaxies are ripped apart. The Milky Way, Andromeda, all the great spiral and elliptical galaxies, they fragment as the expansion overwhelms their internal gravity. Stars are flung into intergalactic space. 3 months before the end, solar systems disintegrate. The Earth is torn from its orbit around the Sun. All planets become rogue worlds, drifting alone through space that's expanding faster than orbital mechanics can maintain. 30 minutes before the end, planets themselves fragment. The Earth would crack and shatter, its internal structure unable to withstand the expansion of space itself. Rocky worlds crumble, gas giants disperse. In the final fraction of a second, atoms split. Molecules shatter first, then atoms themselves are torn apart, their electrons ripped away from their nuclei. Then even atomic nuclei disintegrate into their constituent protons and neutrons. And finally, in the last instant, even protons and neutrons themselves are torn apart into quarks and gluons. The fundamental building blocks of matter are destroyed. The universe ends not in heat death's slow fade, but in a violent unraveling. The fabric of reality itself tears. And then, what? The equations break down. Physics ends. Nothing can be predicted beyond that point. The Big Rip seems less likely than heat death, based on current observations, but it cannot be ruled out entirely. The evolution of dark energy is one of the biggest unknowns in cosmology. If dark energy is quintessence, a dynamic field rather than a cosmological constant, it could strengthen over time, and if it does, the Big Rip is our fate, not in billions or trillions of years, but potentially in as little as 22 billion years, tomorrow on cosmic timescales. Faced with these dire predictions, physicists have proposed numerous theories, attempting to make sense of dark energy and perhaps find hope in the mathematics. The simplest explanation remains Einstein's cosmological constant. Empty space has an intrinsic energy density that's constant everywhere and for all time, mathematically elegant, observationally consistent, but fundamentally unexplaining. It doesn't answer why the constant has the value it does. Quintessence theories propose that dark energy arises from a scalar field permeating space. Unlike the cosmological constant, this field field can vary over time and space. Different quintessence models propose various shapes for the field's potential energy. Perhaps the field is slowly rolling down a gentle slope. Perhaps it's coupled to ordinary matter in subtle ways. But quintessence models face their own challenges. Current data shows little evidence that dark energy is changing at all. If quintessence exists, it's evolving very slowly. Modified gravity theories propose changes to Einstein's equations that become important over large distances or low accelerations. In these models, there is no dark energy. The accelerated expansion is a consequence of how gravity operates on cosmological scales. But these theories struggle to explain the full range of observations. The multiverse hypothesis offers a radically different perspective. If our universe is just one bubble in an internally inflating multiverse, then different bubbles could have different values of physical constants, including dark energy. We observe the value we do because we exist in a bubble where that value allows for structure formation. This is the anthropic explanation. It doesn't predict dark energy's value from first principles. It explains why we observe this particular value, because in universes with radically different values, we wouldn't exist to observe anything at all. String theory describes particles as tiny vibrating strings in higher dimensional space. The cosmological constant is determined by the shape and size of extra dimensions. But string theory allows for an enormous number of possible configurations, perhaps 10 to the 500th power or more. Each configuration would give a different value for dark energy. Some theorists have proposed that dark energy and dark matter might be related manifestations of the same phenomenon. Perhaps they interact in subtle ways. But so far, no compelling unified theory has emerged. Another speculative idea is that our vacuum might be metastable, existing in a false vacuum state. What we call dark energy might be the energy difference between our current vacuum and the true vacuum of lowest energy. The universe might eventually tunnel to the true vacuum, releasing energy and changing the laws of physics. This connects to vacuum decay scenarios. If the vacuum can decay, then dark energy is not just driving expansion, but potentially threatening existence itself. Yet another approach questions whether dark energy exists at all. Maybe we're in a unique region of the universe. Maybe our measurements are systematically biased. These alternative explanations face significant challenges. The observations of accelerated expansion come from multiple independent methods, all pointing to dark energy's existence. The diversity of theories reflects our deep uncertainty. Every theory is trying to bridge the gap between observation and understanding. But so far, every theory has its own problems. The cosmological constant is too fine-tuned. Quintessence is too unconstrained. Modified gravity conflicts with observations. The multiverse is untestable. We're left with possibilities, none fully satisfying. Perhaps dark energy is telling us that we've reached the limits of what can be understood with our current tools. Perhaps reality is fundamentally stranger than any theory we can construct.
While theorists propose explanations, observational astronomers have developed tools to probe dark energy's properties with unprecedented precision. The James Webb Space Telescope, launched in 2021, is the most powerful space telescope ever built. With its infrared sensitivity, Webb can observe the earliest galaxies forming in the ancient universe, helping us understand how galaxies evolved under dark energy's influence. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, is specifically designed to study dark energy. It will survey billions of galaxies, measuring their positions and shapes to map how cosmic structure has evolved. It will discover thousands of supernovae, tracing the expansion history with great precision. The Vera C. Rubin Observatory began operations in 2023. This facility will photograph the entire southern sky every few nights, creating a time-lapse movie of the cosmos. It will discover millions of transient events, providing unprecedented statistics for dark energy studies. The Square Kilometre Array, a network of radio dishes across multiple continents, will map hydrogen gas in distant galaxies, providing another window on cosmic structure and expansion. Gravitational wave detectors like LIGO and Virgo observe ripples in spacetime from merging black holes and neutron stars. The propagation of gravitational waves through expanding space is affected by dark energy. Future space-based observatories like LISA will detect mergers of supermassive black holes across cosmic history. Particle physics experiments search for dark energy in the laboratory. If quintessence fields exist, they might interact with ordinary matter through forces weaker than gravity, but potentially detectable. Experiments at Fermilab and CERN look for tiny deviations that might reveal these interactions. All these tools share a common goal: to measure dark energy's properties with such precision that we can distinguish between different theoretical models. Is it constant or evolving, uniform or varying, interacting with matter or purely gravitational? Each new measurement refines our understanding. Each survey discovers phenomena that challenge or confirm predictions. But with each answer, new questions arise. The Hubble tension suggests something unexpected in cosmic expansion. Anomalies in the microwave background hinted features we don't understand. The tools keep improving, the data keeps accumulating, yet the fundamental nature of dark energy remains mysterious. Perhaps the next generation of instruments will provide the breakthrough, or perhaps we're still missing some crucial piece of the puzzle. But beyond the science, beyond the measurements and theories, lies a deeper question. How do we live with this knowledge? Because knowing the universe's fate affects how we see ourselves and our place in existence. Dark energy delivers perhaps the final blow to human ego. Not only are we insignificant in the vast cosmos, but that cosmos is temporary. Everything we are, everything we've done is being dissolved into nothing by an unstoppable force. Different people respond differently. Some experience existential dread, cosmic anxiety. The universe is too big, too empty, too meaningless. Why do anything if it all ends in heat death? Others find strange comfort in cosmic perspective. Yes, everything ends eventually, but that makes the present moment more precious, not less. We exist now in this brief window when the universe is knowable and life is possible. That's miraculous. Some embrace cosmic nihilism. Nothing matters ultimately, so nothing matters now. But this can also be liberating. If nothing matters cosmically, we're free to create our own meanings without worrying about cosmic validation. The knowledge carries emotional weight. Understanding that the universe is expanding into nothing requires emotional processing as well as intellectual understanding. Some experience existential vertigo when first deeply contemplating these ideas. Everything seems less solid, less permanent, less meaningful. But for many, this eventually gives way to acceptance or even appreciation. The universe is what it is. We're part of something vast and ancient and doomed. That's not our fault. We're just here to witness it, experience it, understand it as best we can. And perhaps that's enough. Perhaps witnessing itself is meaningful. Perhaps consciousness arising to understand its own cosmic context is the universe's way of justifying itself. We can find purpose in the pursuit of understanding. Every observation revealing something new about dark energy, every theory explaining another aspect of expansion is a human achievement. We're trying to understand the universe despite being tiny, temporary parts of it. That's heroic. Science becomes a form of defiance. The universe is indifferent, but we care. The cosmos races toward heat death, but we try to understand why. Dark energy pushes galaxies apart, but we measure the acceleration. We're asserting that knowledge matters, even in a universe destined for entropy. We can also find meaning in connection with others. If the universe is lonely, we don't have to be. Every relationship, Every conversation, every moment of genuine connection is a small rebellion against cosmic loneliness. Art, literature, music, all forms of creative expression take on new significance. They're ways of asserting that beauty and meaning exist despite the universe's indifference. We create beauty knowing it won't last, which makes the creation all the more poignant. We've now confronted the architecture of doom. We've seen how the universe will end, whether in the slow fade of heat death or the violent rupture of the Big Rip. We've explored the theories attempting to explain dark energy and the tools measuring its effects. We've grappled with what this knowledge means for human meaning and purpose. But one question remains, the deepest question, the one that haunts every physicist who studies these phenomena. What lies beyond everything? In our final journey, we'll confront the philosopher's void, the nature of nothingness itself, the question of what the universe is expanding into, and the final emotional weight of living in an expanding cosmos, aware of the abyss but not defeated by it. We'll explore whether consciousness can survive cosmic death, whether meaning persists in the face of heat death, whether there's hope in the mathematics of doom. We've learned that the universe is dying. Now we must learn how to live with that knowledge, how to create light in the expanding darkness, how to find meaning in the void. The final chapter awaits, the one where science meets philosophy, where terror meets wonder, where nothing meets something in the eternal expansion. To be continued in Part 4, The Final Question, where we explore the deepest philosophical implications, the emotional weight of infinity, and what it means to be conscious in an expanding void.